Good afternoon, fellow foundrymen. This is Sendil Kumar, Secretary from IF Chennai Chapter. Before we get started, I'm requesting everyone to put yourself on mute, and maybe you can also switch off your camera, and we can give a full attention to the speaker so that there will not be any disturbance. And it gives me immense pleasure to interact with you for yet another our weekly webinar, and this is our Chennai Chapter webinar in jointly with Southern Region. I'm sure that people who have joined from Chennai are safe and recover to the normal activities. And we had a very bad time this week. I'm sure that of it. Today we have very interesting topic: optimizing and magnesium treatment process in ductile iron, the cost-efficient approach. This is one of the important topic which is I could feel by the even number of participants. The topic has invited many people. Generally, we get people joined a little late. I think even before program starts, I could see the number of people who have joined. Numbers are getting increased. And thanks for everyone to join here. To start the program, I'm requesting our SR Chairman Sanjit Pittur sir to formally welcome the gathering, please.
Yeah, thank you, Senthil. Good afternoon, everybody. It's my honor and privilege to welcome you all for this webinar, which has been jointly hosted by IF Southern Region and Chennai Chapter. I think in today's time, Chennai Chapter has really done a great job by having an apt webinar that they have conducted, optimizing magnesium treatment process in ductile iron, a cost-efficient approach. I think in today's time, when we say that our customers don't increase the prices of the castings, I think it's our duty to in-house that we reduce the cost and make money. Gentlemen, I welcome today's speaker, Mr. Balaguru Sendil, Deputy Manager, R&D, Elkem, South Asia Private Limited. Welcome, sir, for this webinar. And I hope, as Senthil said, all the people from Chennai are doing good after the cyclonic effect that we had on last Sunday and Monday. So, gentlemen, relax and just have a good of the seminar. Thank you.
Thank you, sir. Thank you very much. See, generally the topic is a more important thing, and we also need to know who is delivering about the topic, and we should understand the man behind the lecture. And Elkem is known to everyone, and Mr. Sendil is also known to many of the people in this forum. But as a customary, we need to introduce it to him. I now request our Chennai Chapter Chairman, Mr. V.K. Ramans, to introduce the speaker of the today to the forum, please.
Yeah, thank you, Sendil. Am I audible?
Yes, sir, you are audible, sir.
Good afternoon, Chairman.
Good afternoon.
Good afternoon, Mr. Balaguru Sendil. So it's my immense pleasure to introduce Mr. Balaguru Sendil to this August gathering. And the topic and all already explained by our Secretary and the SR Chairman. So presently, Balaguru is working as Deputy Manager R&D, TCS Foundry, Elkem Innovation, and a strong engineering professional with a Master of Technology degree specializing in foundry alloy production. He is also a qualified research professional with 9+ years of applied research experience in foundry metallurgy and metal treatment. Presently working with Elkem as part of their global foundry innovation team, involved with numerous innovative projects in the design and development of optimized metal treatment alloys for the iron industry. And his area of interest are thermal analysis of cast iron, metal treatment solutions for specialty SG and CGA iron castings, conceptualizing and designing innovative 3D parts and assemblies using CAD tools, process optimization using statistical tools. So with his widespread area of interest and experience, Mr. Balaguru is going to share his knowledge to enrich our present level of understanding about magnesium treatment. Definitely, this will give good amount of benefit to all the fellow foundrymen. Now, I request Mr. Balaguru to take it further. Thank you.
Thank you, sir. Balaguru sir, stage is yours. Please take over, sir.
Okay, sir. Thank you. Hope I'm audible and clear to everybody.
Yes, sir. You are audible.
Yes, sir. Once again, thank you for each and everyone for taking the time and effort to be here on a Saturday evening to spend time with us to gain some knowledge. Hopefully, at the end of this session, I'll be able to add some value to your time and resource. Before I begin, as a customary, I would like to thank all the IAF office bearers, especially the Chennai chapter bearers, who have provided me this opportunity to be. It's a back-to-back opportunity. Couple of weeks back, we also did a seminar, so it's quite nice to meet all the people in on an online platform. So before I start sharing my screen, this is something that I wanted to share. I will switch off my camera, and then if you have any questions, please feel free to ask at the end of the session, because I have only one screen. I will not be able to see the chats, or if somebody interrupts also, I will not be able to respond correctly. So I would request everyone, if you have some comments or questions, you can always post it towards the end. I would start sharing my screen now.
Yes, sir. Sir, I'm requesting other
One request,
delegates of your mobile, your
participants are
audio
requested to
video.
switch off the video.
Yes, sir. Sir, participant can you can switch off your video, sir, so that the focus can be given to the presentation.
So just a minute, sir. I'm having it's not sharing. Just give me a couple of minutes. Apologies for this. So I will start the topic. So today's topic, what we have chosen is that when it comes to ductile iron, we are quite familiar with how to produce ductile iron, the different grades. Most of the foundries in India are capable of producing it, but there's always a scope for improvement, how we can optimize the process. At the end of the day, we can save a lot on money. And also magnesium is quite not abundantly available material as such, and it is very not an environment friendly process for the production of it. So in the greater scheme of ESG and in the greater scheme of environment friendliness, it is always better to use less and get the maximum benefit out of it. So I have devised this presentation in that way. What are the different options we can do for nodularization process? What is nodularization first? The different options that is available and which is the best for your application, for your foundry, and for that particular type of casting. And this is something that I would like to cover today. Pushing to the next slide, we have seen a microstructure like this. People who are making ductile iron, people who are continuously checking the quality of it, since most of the foundries do it. If you're taking a base metal, pouring a micro sample and see, you will see something like this. The microstructure is quite, so this is the base metal, how it looks like. We are having some amount of carbon in our system, and then we are having iron and silicon. There is only certain amount of carbon that can go into your iron and silicon system. Rest of the carbon that you are voluntarily adding to your iron and carbons, I mean your iron and silicon system, will be thrown out. If you look at the typical iron carbon diagram, something more than 2% of carbon is the maximum solubility for a particular silicon level and an iron level. Rest will come out. Since we are having carbon in our base metal, if this is not coming out properly, you will get something like this. This sort of microstructure is quite hard, brittle. It is very difficult to use this material for any engineering applications. Again, going for the, as I was saying, the base metal, if you look, the microstructure is something like this. But with this microstructure, it will be very difficult to have any engineering application. As such, this material is quite hard and brittle. But when we are producing ductile iron treatment, we do a lot of magnesium treatment. But what happens is that when you do the magnesium treatment also, the second microstructure looks something like this. You see a bit of nodules, but most of the time there's a lot of carbides. So again, this has improved the mechanical properties to some extent, but again, this is also not quite usable. And the next one is that after magnesium treatment, when you are going for an inoculation practice, that is where you see very nice nodules formed. And you have very nice nodules formed. And this is the microstructure that we want, so that we will be able to use for a lot of engineering application. Based on how this microstructure changes, we have different mechanical properties changing. We have various tensile points and various hardness values, which we use for different grades. And these different grades are used for different applications, ranging from engineering, automotive, all the way to constructions, nuclear waste storage, etc. and etc. So this is how a typical ductile iron microstructure looks for the base metal after treatment and after finally inoculated and in your castings. So what is happening in each of these stages is quite interesting to know, because once we know the fundamental of it, it helps us to optimize it further. So the next part is that, so as we discussed, that we need to change a lot of the way the microstructure looks from your base metal and after adding magnesium and after doing inoculation. And that is how we do a lot of value addition to our process, so that you'll be able to add the better microstructure, which gives you a better mechanical properties, which makes your casting more usable. So the next one is carbon. Why I have put carbon is that, as I said earlier, the iron and silicon goes into your system. The carbon is something that is coming out of your liquid metal because of the solubility issue. The way the carbon comes out is very important. At what time it comes out, at what shape it comes out, at what size it comes out is also very important to get a very good microstructure. So why carbon is basically an allotrope? I mean, I'm not trying to go into very much basics here, but this is something that it's easy for us to understand and realize what is the logic. Allotrope means that it can exist in more than 2 or 3 different crystal structures depending upon the conditions. But as said, carbon is a crystal, so it has 4 different families that are most commonly available. One is a graphite. Normally, we are using it in our microstructure. What we see, we want the carbon to come out as graphite. We make a lot of effort to make sure that the carbon is coming out as graphite and not as carbides. So other form of carbon that can be naturally is diamond when it gets pressed a lot. And there are a few other forms also available, but these are used for very hard and brittle engineering applications. For cast iron perspective, for ductile iron, we are only interested in graphite. As I said, the graphite is a crystal. What do you mean by crystal here is that these are all arranged in a perfect manner as they are cooling down. When they are in liquid, they are randomly oriented, the atoms and molecules, but when they are beginning to solidify, they form a very perfect, they have a very nice structure orientation. They are very structured. That is why it's a crystal structure. And as I said, what is the structure that it is following? It is basically a hexagonal cell. So why we are saying this here is that when we go deep into analyzing what is a nodule, I will show it later in the upcoming slides. The orientation of all this is very clear. So in ductile iron, we have millions of these small hexagonal cells, which actually forms the nuclei. The nuclei in turn make sure that the carbon is coming and growing there, which we call it as nucleating sites. The other term is nucleation. So we have millions of these formed. So what happens here, if you look at it, as I said, it is a hexagonal structure. So this is the structure in which the carbon is arranged when it begins to cool down and solidify. So when it is arranging in this particular hexagonal structure, it wants to grow further because more carbon is coming and depositing. The somewhere between 2 to 3.6, 1.6% of carbon that is floating around wants to come and deposit somewhere here. So what happened because of this shape of this hexagon, it can go only in 2 directions. It can go in a basal direction, which is in this way, or it can go in a planar direction, which is on the top. So depending upon which grows faster, we get a nodule. For instance, if this axis is not growing faster and this axis is growing faster, then we get a nodule. The carbon keeps depositing on top of this each other, and then it forms a nice nodule. But unfortunately, if this connection is getting grown faster, then you will have the x-axis growing faster and not the y-axis, and then you will get a very nice flaky structure. If the basal growth is faster, you get a flake. If the planar growth is faster, we get a nodule. So this is the logic in which the carbon, when it is getting stored or coming out as graphite, it forms this hexagonal structure, and this hexagonal structure, the way it is growing, it determines whether it is a flake graphite or a nodular graphite. So what we have to do is that we just need to adjust the speed or the growth velocity, which is growing fast, whether this axis is growing fast or this axis is growing fast. If you are able to control this speed or the growth velocity, you will be able to determine the shape of the graphite. It can be a flake or it can be a nodule. So for doing that, we just need to control. And how do you control? You do nodularization process. What does nodularization mean? It is a process of introducing magnesium, which makes sure that the speed of this particular plane, that is the planar, is growing faster than the basal. So the speed difference is very critical to form a very good graphite shape. So this is the basics in which the nodule grows. And whenever we see there is a mismatch in this growth rates, you get a degenerated nodule, which kind of doesn't have any useful mechanical properties. So again, going to the topic of nodularization. So this is a microstructure what we have seen. We have seen that the structure, this is an actual image of a nodule at a very extreme magnification of 70,000x, which is taken in Elkem. So this you can very clearly see how does the nodule look like, the core of it. So again, what does nucleation? So nucleation, as we discussed earlier, is the general term describing the formation of graphite growing sites. Basically, this is a site on which the graphite starts to grow. So it is the formation or the creation of sites on which the carbon which is coming out and wants to settle somewhere and be stable. If you have these nucleating sites, the carbon will voluntarily come and settle there and come out as graphite. Unfortunately, if you don't have enough of these sites, then the carbon can come out as carbides because there is not enough of graphite growth sites formed. So how do you influence the amount of nucleation? There are many factors which influences it. The most common is the charge composition, what we are following. It is your carbon equivalent. How much is your carbon and silicon? So this is the most basic thing that can influence it. The second one is your melting practices, the furnace that you do, the charge mix that you follow, the sequence that you use, the amount of holding that you have. All this will impact this effect of nucleation. If you are holding it for more, then the nucleating sites that the base metal inherently has will get depleted over a period of time. Again, how do you do the treatment process in case of ductile iron? You are doing a nodularization project, I mean a process. So your base metal has these nucleating sites. If you're holding it for long in the furnace, this will get degenerated. Again, when you're doing treatment process, as we saw in the first couple of slides, after treatment, the microstructure doesn't look very great. So again, it is very important. What is this treatment process? How you are going to introduce this nodularizer is very important. What happens is that if you're not able to control this graphite growth sites is not controlled, if it is growing excessively, then you get a degenerated graphite, you get exploded, chunky, all these issues will happen. But if it is not at all growing, then you can get carbides because there is not enough places for the carbon to come and settle. It can become carbides. When this happens, it will strongly influences the mechanical properties. When the mechanical properties gets changed, then the casting will get failed or rejected, or it can have a lot of machinability constraints. So it's always more nucleation is equal to greater graphite growth. You no need to have too much amount also. Excess amount of nucleation is also a problem. This happens when you have a lot of unwanted elements, heavy elements, slag, dross goes into it. There's a lot of excess nucleation that happens. So this is very critical. If you look at it, the core of it, the schematic which I showed in, I mean, the actual image what I showed in the previous slide, and this one, if you see, the core is always a magnesium sulfide and a calcium sulfide when it comes to ductile iron, and it has a silicate shell. So this is the element that what we have seen physically in Elkem using our equipments. So what we have seen here is that gray iron typically looks like this. We know that this is a very good gray iron microstructure. And when you do nodularization, you get a ductile iron microstructure like this. So what is a nodularization? What you do is that you have to use elements which can actually help in changing the speed. In the second slide, we discussed that the growth rate between the basal and planar plane has to be having a certain equilibrium. If that equilibrium gets distorted, then you will not get correct amount of nodules. You will get flakes in between, you will get CJ, all these things. But how do you know, how do you are able to alter the speed is through having some elements like magnesium, which will actually monitor the speed, which is a very simple terms. I'm saying there's a lot of understanding behind it. Cerium is also another element which can actually influence the speed between the basal and planar growth rate so that you end up getting a nodule. The other one is lanthanum. These are three of the most common elements which can influence the process of nodularization. There are a few other elements also which can influence the conversion of a flake to a nodule, but those are not quite commonly used in a large scale commercial setup of making ductile iron. So these are the elements we know, but how do you introduce these elements? You need to have some sort of a carrier medium so that these elements are going and doing its effect perfectly. So what are the agents which something that is used for carrying these elements and dropping it into the system? One as such is pure magnesium metal. We are getting magnesium ingots that can be used directly to our ductile iron treatment. It has its advantages and disadvantages. The other one is ferrosilicon magnesium, where you have magnesium combined with iron and silicon. Both of these acts as a carrying element and then make sure that the magnesium is coming into the liquid metal during treatment at a controlled level. And the last one is mish metal, which is also used. Mish metal is a combination of rare earth. The rare earth most commonly present is cerium and lanthanum. This can also be used as a nodularizing agent. So these are the various elements that is causing the effect of nodularization. How they are causing that effect is that they are able to adjust the growth rate between the basal and planar plane so that you get a nodule. But how do you introduce all these elements? These are the sources in which these elements can be introduced. The next one is that magnesium treatment. So when you are doing magnesium treatment, what happens is that I've showed you the schematic structure. What is a nodule? In the core of the nodule, you have a magnesium sulfide and a magnesium oxide core. So the magnesium, what it does, it goes and reacts with your sulfur and oxygen in your metal. So that is why for magnesium treatment, for a good magnesium treatment, you need to have some amount of sulfur. Most of the ductile iron foundries focus heavily on making sure that the sulfur is not going beyond a certain limit, a 0.02 or 0.015, whatever is the control limit that they are having. Sometimes they tend to overlook the phenomenon that they don't need to have any amount of sulfur. You need to have certain amount of sulfur in your metal, which would actually help in forming it. If you are having extremely low sulfur in third decimal, then it will be very difficult to do a good nodule rising process. So what happens is that this magnesium reacts with the sulfur and oxygen. And unfortunately, what happened, we discussed in the previous one, we need to form this MgO and MgS. These are the components that are readily formed. But if they are quite big in size, then it becomes a slag and it goes out. And then we have creating nucleating sites. These nucleating sites help the graphite to come and settle down there. So these nucleating sites, we have measured it. It is approximately 1 micron in size. These are very small. So again, the size matters. How does the size keeps growing? If you are holding it for longer after treatment, the size keeps growing. The nucleating sites accumulate together. They come out and float out as slag and then goes out. That is why you see a gradual fading effect from the start of pouring towards the end of pouring. So this is what happens if you have magnesium that reacts with your sulfur and oxygen. It forms these nucleating sites of MgO and MgS. But this MgO and MgS also constantly, they are 1 micron in size. They are very stable, but unfortunately, if you are having more amount of magnesium is added or more amount of sulfur is added, then they have the chance of getting formed together, agglomerating together, and then moving out. So basically, nodularization is nothing but you're doing desulfurizing and deoxidizing. So this is the basic fundamental of magnesium treatment. The most key factor from this here is that you need to maintain a minimum amount of sulfur. If the sulfur levels goes beyond certain level, then that is also a risk. If it is coming below a certain level, also it is risk. So ideally, you should have a target of 0.008 to somewhere between 0.015 in your base, which is the correct amount of magnesium required. When you have excess amount of sulfur, then you need to have a higher magnesium. I will come down to all that in the later upcoming slide, but this is the basic of how the magnesium treatment happens. We know when we are introducing magnesium, we are able to alter the speed. How does the speed alteration happens? It is able to control both the sulfur and oxygen and able to have a better nodule counts or nodularity, sorry. So this is an optical microscope typically at 100x what we have seen. And the second one is a nodule at a scanning electron microscope at 1000. It looks very something like this. It's very difficult to justify what it is. But we have seen it at 70,000. This is the one that I showed in the earlier slides. So we have gone up to a magnification of 70,000 and then we have seen this looks something like this. So what is the element that is present in there? So we were able to do an XRD mapping, sorry, and then we were able to see what is the core and what is the outer oxide layer that is formed. So based on this only, we came up with this schematic diagram, and this has been there established by Elkem team members almost 30-40 years ago, and still it is not being challenged or it is still being validated yet. And this holds today. This is a very strong theory that what we have, and this also helps us in developing our product as well as in process and optimizing it. So this is the way we see from Elkem, how does the nodularization process happen? and also what is the core of a nuclei and what is the shell of the nuclei and how this is actually helping in making sure that the carbon is coming and settling down there and it is growing to the correct size and shape. You don't want to have a misbalance in this growth rate, otherwise you will end up getting degenerated nodules which will not have good mechanical properties. So again, this is what happens when this is the microstructure we saw in the first slide. When we are doing magnesium treatment, we are creating enough of these nucleating sites. We are creating magnesium sulfide and calcium sulfides on oxide shell is what the core is always magnesium sulfide and calcium sulfide. Some sulfides we have majority magnesium sulfides and it has an oxide core. What happens is that when after you are doing inoculation, this particular area replicates, there is a lot of vacant sites here. If you look at it in terms of more depth, this sites vacancy, what it has, it mimics that of the carbon and the carbon can come and start depositing here. And since it is of this magnesium sulfide core and then we have this silicate oxide, it kind of grows into a nice uniform nodule. This keep building up in a layer and you get a round nodule. What happens? Magnesium treatment makes the nuclei particle, inoculant makes the nuclei effective for graphite nucleation. That is the growth of the graphite. So that is why when you're doing magnesium treatment, you see a lot of these sites, but these sites are quite small. The graphite is not come and settle down there. A subsequent inoculation will make sure, the correct inoculation will make sure that you have very nice carbon growing in the correct shape and size to have a very perfect nodule. Again, we discussed here, this is the structure that we showed in the first couple of slides. So if you look at it, this is the hexagonal structure of the carbon that is having there. And this is growing at, this is a direction, A direction, and this is the basal direction. And this is the planar direction. So in this, so if you look at the distance between these two is about 0.671 nanometer, and this is about 0.246. If this 0.246 keeps going at a faster rate, you get a flake. If this keeps growing at a faster rate, you get a nodule. But for forming a nice nodule, we need both of these to grow at a correct rate. You need to have a equilibrium. You don't want to completely eliminate this growth. This also needs to grow. So that is why an equilibrium between both these basal and planar growth needs to be achieved. So that is why your FSM, what you are adding, should be very critical. Each nodule that you produce is actually it undergoes a lot of logic. It undergoes through a lot of transformation before it is being produced. So as a foundryman, you should feel extremely proud that each nodule that you produce goes through a lot of effort and metal structure has a lot of changes that is happening. But you see here, this is very nice to see here that, okay, I need to grow this faster, I need to control this faster, but all this has to happen in less than 200 seconds. So it's a very fast thing that is happening. And also at the same time, the metal is also cooling because of the external heat that is being released. So this all has to happen very fast, very quick at the same time when it is cooling. So that is why it is very important to have the correct treatment process, the correct treatment package to make sure you have a very good microstructure, a uniform microstructure across your casting. Is this equilibrium, the VA and VC, this is the velocity that is glowing in the A axis and the C axis. If this gets direction, C is basically your planar and A is your basal. If this gets distorted, you get graphite degenerations, and we have many graphite degenerations you have seen here. I have just briefly put it into here, the various types of defects that we have. So what I have tried to highlight it in yellow are something that can be related to your treatment process. If this gets disturbed, all these sort of defects can come. So apart from not only consuming more amount of magnesium, more amount of inoculant, if there is a misbalance happening here, you would also get degenerated graphites, which is again your metal rejections, again your machinability concerns, again your whoever owns machine shop might face that my tool life is getting worn out easily or faster. All these things will come up. This all can be correlated to your treatment process. So what are the different treatment options that we are having at the moment? The most common one is what I have put in. I have not put in all the treatment processes. The one that is most commonly used in the industry. So the options that what we have today, most prevalent in India as well as globally, is that we have an open ladle where you put the ferrosilicon magnesium here and then you tap the metal from the top. Some people started using a pocket where you have make a small pocket, you put a ferrosilicon magnesium and a cover. I have seen foundries where they put inoculant also in between. That is also a practice being followed, but it can be always questioned and challenged. The next one is to have a tundish. where you have the pocket here and you put the treatment alloy, which is a combination of ferrosilicon magnesium and a cover, and then you have a tundish on the top with a hole. So this is process is called as a ladle treatment alloy process. In this, you can use ferrosilicon magnesium, nickel magnesium, and a few other alloys. And then we have pure magnesium converter, where you have a ladle which is placed in this orientation. You put the magnesium, pure magnesium here, and then you tilt it. This reacts very violently, and you can get the nodularization effect happening here also. The other one is the in-mold FSM process, where you have a chamber that is put into your gating system itself, where you keep the ferrosilicon magnesium inside the mold, and then you just pour the metal and then you just cast it. So this is one of the most efficient way of doing it, but it requires a lot of process control. And the last most common, or the one that is there in the market for a long time but suddenly gaining momentum, is cold wire. So I will briefly touch upon all these options what we have. So if you go for the pure magnesium converter, as I told here, you have the option of putting the magnesium, pure magnesium ingot alloy here. People have modified this and also started putting ferrosilicon magnesium here and tilting it. It has its own advantages and disadvantage. So what happens here is that it is best suited for large size treatments. So when you're using pure magnesium, what is there? The magnesium can only have MgS and MgO. These are the two compounds that can form, because we don't have any other. The magnesium is 99% or 100% nearly pure metal. There is no other element present here which is going to help the case of nodularizing. These are the two compounds that can form. But unfortunately, what happens? Magnesium starts melting at 650 degrees Celsius. You are going to pour it around 1400 degrees or 1500 degrees Celsius, depending upon how long do you want to pour. But the magnesium starts melting at 650 and it starts boiling at about 1090 degrees Celsius. So the reaction fumes will be very violent. What happens here is that the magnesium content or the purity here is 100%. The recovery is extremely low because the reaction violence is so much. More, if you want to have 0.045 amount of residual Mg, the amount of pure magnesium you have to add is extremely on the higher side. And it is also completely kills your base metal in terms of having any inoculating effect. You need to add a lot of inoculants after that to make sure that whatever nucleating site this pure magnesium has used comes out as a useful nodule. Again, the EHS environment risk is quite high because it is very high and volatile. It can blast anytime if there is some maintenance issue that has been overlooked. The other one, the capital required is also quite high. But one advantage is here is that the base sulfur restriction is not there. This is especially used people who are bringing metal from, people have converted from cupola, but still some of them who are using cupola. This is a very useful tool for them. And they can use this for getting the, I mean, if base sulfur is more than 0.03 and they want to do duplexing in induction furnace, if they don't want, then pure magnesium is a good option. Again, the treatment size has to be on the higher side. If it is for 500 kg, 600 kg or a 1-ton treatment, it will be very difficult to justify the cost of using this particular process. The second one is that using ferrosilicon magnesium. So what does ferrosilicon magnesium does? Apart from that usual magnesium, which can combine magnesium sulfide, which is what the core of it, we have calcium also in ferrosilicon magnesium. We have rare earth also in ferrosilicon magnesium. These are the various reactions which can help in nodularizing that can happen. So this is the much more stable approach than having a pure magnesium as a source of nodularization. So FSM is directly and indirectly used in where we have ladles. We have different types of ladle, open ladle, tundish ladle, pocket ladle. All in this, we can use ferrosilicon magnesium. In the in-mold ferrosilicon magnesium treatment, in-mold FSM treatment, there also we are using ferrosilicon magnesium. Interestingly, in code wire also people use ferrosilicon magnesium. The code wire, the wire what you see inside has some amount of ferrosilicon magnesium fines inside it. Because if they use pure magnesium alone, it will be very difficult to have some reactional advantages what you're getting here. And if you look at the microstructure of a ferrosilicon magnesium, this is how it looks. This is an image from SIM. We have done EBST, and then we have seen what are the different phases that are there. There in the previous slide, we saw only magnesium, which starts boiling at about 610 degrees Celsius. I mean, it starts melting at 600 degrees Celsius and boiling at about 1100 degrees Celsius. But in ferrosilicon magnesium, you have iron, silicon, magnesium, sometimes cerium, sometimes lanthanum, sometimes calcium also. It's highly customizable to as per the foundry need. If you look at it, the ferrosilicon as such is a carrying element. It has a very high melting point. How this is impactful is that when you are doing the ductile iron treatment, this will make sure that the reaction starts very late. So more amount of metal is going into your treatment ladle. And the ferrosilicon FeSi2, it has a slightly lower. And then we have the magnesium Mg2Si, which is it starts about 1080. So you could see here that in pure magnesium is about 600, this is about 1100. So this is the impact of having silicon and iron in your FSM. And then we have calcium, magnesium. This has a very high melting point. If you look at the distribution of it, majoritively will be iron and silicon, FeSi2. These are the phases that will be formed in all your ferrosilicon magnesium. And this Mg2Si and then calcium, magnesium, silicon. This again will be very less because the amount of magnesium in your ferrosilicon magnesium is not more than 7 or 8 or 9%. Again, how do you get this microstructure is also very challenging. People who are making ferrosilicon magnesium who will know that it is very challenging to get a uniform distribution of all these phases. So it's a lot of challenge to control this, because this is why you see a very natural segregating. You might get a ferrosilicon magnesium at a cheaper rate, or you might get a substantial product where you would not see this much amount of magnesium. You would see a lot of being spent only here. The distribution is completely segregated. You will see not Mg2Si or calcium, magnesium, aluminum silicide. You will just see magnesium segregated out. Because of the way they produce it, it will again not perform as good as a uniformly distributed one. So this is the FSM alloy. If you're using ferrosilicon magnesium, these are all the positive reactions that will happen, which will help in your nodularizing effect. When you have all these reactions happening, you no need to have so much amount of magnesium. Your recovery always improve. In pure magnesium, you get about 30 to 40% recovery. With FSM, you can expect somewhere between 60 to 80% magnesium recovery. And in mold FSM, you can expect more than 85 to 90% of magnesium recovery is possible. In ductile iron, as I said, the major elements, something is magnesium is the major element. What does? It ties up the sulfur and oxygen. It creates the nucleating site with MgS in the core and then oxide shell, which makes sure that you have the nice graphite growth happening in that nucleating site created with the help of magnesium. And it nodularizes the graphite. Basically, it makes sure that it adjusts the speed, and then it makes the graphite round and very spherical in shape. It unfortunately it increases the chill tendency. That is why if you are adding more amount of magnesium, if you are having a 500 kg treatment size, just to save on cost, instead of using a 6% magnesium, if you are going for a 9% magnesium and reducing the addition percentage, you are actually using more amount of magnesium, which goes free into the metal, which is not using in helping in this which is not helping in creating this nucleating site, can cause a lot of chill. That is why after magnesium treatment, you see a lot of carbonic structure in your microstructure. Again, it also increases the tendency of slag formation. It reduces the recovery, and reaction violence will be very high. If you are using higher magnesium grade for a smaller treatment, the reaction violence will be extremely high. I would talk about the impacts of reaction violence in the upcoming slides. And the tendency to form slag is also high, because why, I will explain in the upcoming slides. And the next one, what most commonly present is there is rare earth. So rare earth is again the cerium and lanthanum is the rare earth that is commonly present in your magnesium. What does it does is that it also act as an element which is helps you nodularization. We have seen it earlier. And if you're trying to use cerium alone to make ductile iron, it is possible, but it takes a lot of process control, and cerium is not as abundantly available. But pure mish metal is available, which is a combination of cerium and lanthanum. We can use that. Using that 100% instead of magnesium is a challenge. It's not very commercially viable. That is why we have magnesium plus some amount of cerium and lanthanum, which will actually help you in having or the nodularizing process. It does the same as the magnesium. Additionally, what it does, it neutralizes your subversive elements. I am calling subversive elements are trace elements. These can be something less than 0.001 or 0.01 in your cast iron. What does this element do is that it can be manganese, chromium, titanium, boron, vanadium. All these are elements which are in the ppm levels. But these elements can directly impact both the size and shape of your graphite. So these are elements which are very dangerous. There are a lot of other subversive elements can be in your chemistry, but those will not directly impact the shape and size of your graphite. But there are some elements which will impact it. To neutralize all those elements, rare earth can be useful. This rare earth can go tie up all these elements. All these subversive elements, if you categorize them, they are slightly on the heavier side. This rare earth can tie with them, form compounds which are stable, which will go into the solution. It will not come out separately. And it also makes your reactions a bit calm. A calmer reaction is always better. Increases that chill tendency also. It also additionally on top of creating the nucleating site, it also creates an inoculation effect. So this is why Completely avoiding rare earth is also not advisable. It is always good to have some amount of rare earth. That's why FSM you see have multiple grades of FSM and rare earth combinations. So it is always better to keep some amount of rare earth, not always completely eliminate it. The next one is calcium. So what does calcium does is that it reduces your reactivity. The whole purpose of having calcium is to make your reaction much calmer. If you don't have calcium, then the reaction violence is very high. And it increases the tendency of slag formation. And it also creates a very nice inoculating effect. It increases your magnesium recovery. If your reaction violence reduces, your magnesium recovery automatically improves. This is the role of having magnesium, a rare earth, and a calcium in it. The amount of each that has to be there needs to be precisely balanced. This is where the technical know-how Elkem has been producing FSM for the last 70 years. For which grade of magnesium, how much amount of rare earth should I have? How much should I balance it with calcium? There are a lot of other elements that we focus, but for our, intellectual property reasons, we don't disclose that. But this is something that is common knowledge. Again, for a foundry perspective, people who are in sourcing or people who are using regularly FSM, when they are saying that they are offering you a 6 to 7% magnesium, it has to be balanced with your rare earth and calcium. If the calcium is not balanced with your high magnesium and rare earth, then your reaction violence will be not very controlled. Then you will end up getting more slag, most amount is wasted. So these are the most common elements that you have here, and then that needs to be correctly balanced. As I said earlier, pure magnesium starts melting at about 600 degrees Celsius. FSM, the magnesium containing phases itself starts melting about 1100 degrees Celsius. Why? Because it has a silicon effect. If you are just having magnesium and very little silicon, you have a lot of magnesium that just keeps on evaporating and goes into the gas. Nothing is actually going into the liquid metal. Silicon helps the silicon helps bring magnesium into solution in the iron. Otherwise, it just keeps going out and getting lost. Significant influence of magnesium recovery and nucleation. So if you look at it, this is this is the dissolution curve for a ferrosilicon magnesium alloy. You see the curve is like this. So it actually improves the effect. It improves the tendency of the magnesium to actually dissolve into your system, so that more of this is nucleating sites, MgS, is created instead of just it's going out and burning as a slag. So silicon is an important part of your silicate nuclei. We saw the shell, the core is MgS and it is surrounded by a complex silicate shell. So it again influences the amount of silicon that you have. That is why if you see code wire, they use pure magnesium. At the same time, they have some amount of ferrosilicon, magnesium, silicon also into it, because you need to have the magnesium coming into the liquid metal at the correct time, at the correct rate, so that you take the maximum benefit out of it. Otherwise, you are just mechanically forcing something to happen. Out of 100% you add, the recovery will be 30 or 40%. But if you're able to balance the timing in which it comes out, your recovery can obviously go up to 80, 90%. If the recovery goes high, you save a lot of money. Your addition percentage will come down. So this is the impact of silicon, and also the impact of reaction, the reaction violence. So having a calm reaction violence, the first thing is to have a lower magnesium, but your process demands to have certain high amount of magnesium. Then you need to have the correct amount of calcium to balance it. This is in terms of FSM. Additionally, there are a few other parameters also which influences your reaction. The first, reaction violence, fume emission. These are the various parameters that I have plotted here. Slag formation, magnesium addition, magnesium recovery, inoculating effect. So I would term this side as an inefficient process and this side as a efficient process. If your reaction violence, fume emission, slag formation, magnesium addition is all on the higher side, then you are having a very ineffective process. If you are having your magnesium reaction is low, fume generation is low. If both this is low, your slag formation will be low only. In spite of both the reaction violence being calm as well as your fumes also not very extreme high, you are getting a lot of slag. Then you need to check the quality of the FSM that you are using, and also the addition percentage and the size. So if all these are on the lower side, it's a very efficient process. And the next one is the magnesium recovery. People who are working in the shop floor, we know that we get somewhere between 60 to 50 to 60% of magnesium recovery. If it is low, below 60%, that means that there is something wrong. How do you calculate magnesium recovery? We have a lot of formulas available. You take into consideration just the amount of magnesium you're adding, and then what is the residual Mg you are getting. We can go a step further and take into consideration your base sulfur, final sulfur, how much is your pouring temperature, how much is your tapping temperature, which gives you a much more realistic picture of what is your actual magnesium recovery. You need to target at least 60%, and you need to have good inoculating effect. If it is on the poorer side, your process is inefficient. If your magnesium recovery is above 60%, which is good, your magnesium addition will be low, your slag formation will be low, your fumes will also be low, your reaction violence will also be low. So if you're able to get all these things low, it is a much better product. It is a much better treatment process that you are having. It is always advisable to have less is better when it comes to doing ductile iron treatment. The next is the ladle effect. So you are having different types of ladle. This is an open ladle. I've shown you this earlier. This is the pocket one you have. This is a very basic one. The metal stream is hitting here and it is going here. Open, you don't need, sometimes you don't even have this curvature in your lining. We just have a flat ladle, and all these ladles have a nice L/D ratio. This is the length of the ladle and this is the diameter of the ladle. So it always should be in the ratio of more than 2%. The length should be twice that of your diameter. That is the basics of it. But sometimes what happens, people are using more gray and ductile iron. They typically tend to have one common ladle. Most of the ladle, gray iron ladle, they will have a bigger diameter and a shorter height for the ease of handling. In a typical shop floor, it is quite easy to handle. You don't need to have such a high level of shop floor. For ductile iron, it is always advisable to have a tall and narrow ladle. So even in this case, this ladle is an open treatment. This is the pocketed one, and this is the one with a tundish and a proper hole and a pocket alloy cover. So these are the different ladle effect that we are having. I will just show you the effect of sandwich. So we have seen here, this is a sandwich process. You are having a pocket here. You are putting a sandwich. Basically, as the name describes, you have multiple layers deposited on top of it. So if you look at this, this is the typical sandwich. We are putting ferrosilicon magnesium here. The ferrosilicon magnesium is always sold to you in a size range. It is not only one particular size. Why? Because it greatly influences the packing density. You are having a pocket inside your ladle. In that pocket, how much is your volume? The volume can be determined either you can have a tall, narrower pocket or a wide, short pocket. So these are the two ways in which you can design your pocket. The first one is always better. You should have a tall, narrower pocket. But unfortunately, when you have a tall, narrower pocket, if you're not having a correct amount of FSM, you're not following and the scrap is not correct, you have a lot of sticking in the ladle and you need to break the lining fails quite faster. But if you are using a correctly designed ladle, we can help you in having the exact pocket design for your particular application. We have a very nice pocket design calculator, which will be very useful for this. So what happens here is that you have put the FSM here and you have put a cover on top. So it has this flotation point. The metal comes and the entire thing will float up. The other one is the heat transfer. The third one is that control, fusion and reaction. These are the three things that will happen when your liquid metal gets exposed to the pocket. So it will definitely float up to the top. Before that happens, you have a heat transfer happening because the side wall of the pocket will get heated from the metal, and the heat transfer, what happens, it starts to fuse the FSM that is inside here and the reaction starts to happen. So what it does, the sandwich, basically the correctly designed pocket with the correct size of FSM will have a lump fusion. All the lumps will fuse and it will start reacting in a certain correct manner. You will have a controlled reactions. You will have a reproducible reaction, the reaction that what we saw in the earlier magnesium plus sulfur, the rare earth, what we have multiple reactions FSM. This needs to keep producing. This will start melting here. This will again start melting here. So this reaction keeps happening continuously so that more of your metal that you are having in the ladle gets exposed to these reactions, and these reactions will form a very stable nuclei, and that nuclei with subsequent inoculation will give you a very good microstructure. Unfortunately, if there is some mismatch, then you will have the reaction delay. What here I'm trying to say here is that if the sandwich is properly correctly made, you will have the reaction time very slow. You can simply have a process control. Once you start tapping, you can see at what time the reaction starts, the start of reaction. The start of reaction should always happen at least 30-40 seconds. If you're tapping for a minute, entire minute, the start of reaction should always happen somewhere between 40 to 50 seconds. And the end of reaction should always happen after you finish tapping. So if your magnesium reaction stops before you finish tapping, that means your pocket shape is not correct. The size range of FSM that you're using is not correct. It can be optimized. The reaction should stop always after you tapping ends. That is a very basic thumb rule that can be followed by process engineers in shop floor. At the same time, if I want to further improve and cost save on my alloy consumption, then I need to make sure that the start of reaction is as late as possible. One way of doing it is to have a very tall L by D ladle, but we have foundry space constraint. So we maintain a 2:1 ratio, which is good. At the same time, also we have to make sure that the pocket is of the correct size. Again, when it comes to the pocket, we have to make sure that there is pocket life is also very important. We cannot have an extremely narrower because charging of the alloy will also be difficult. So considering all these things, we compromise and we make a correct pocket. At the same time, the other most important critical factor we have to look into is the size of FSM that you are using in the sandwich. What it does, if you have a loosely packed here you see it is, you have the smaller pieces going and settling it here. But unfortunately, if you're using all this bigger size, a coarser or a narrower a size range of 10 to 20, and if you're using a cover, you might get away with it. The cover can go and penetrate these gaps. But if the cover addition is on the higher side of, if you're not able to get good quality consistent cover and you're using a 10 to 20 what happens? This metal space is so high, it kind of penetrates the metal easily. So the entire thing can float up quite fast. It starts to boil. Bigger sites will start quite easily to boil. And it also have this lump, the entire lump can float up. These are the some of the impacts if you don't have the correct sandwich effect. This is a basic L by D what we were discussed here. I have put a formula here. Basically, this D is the hole here. So the tundish you are using, which is well and good. In the tundish, you have a bottom hole. So this hole has to have a particular diameter. That diameter needs to be balanced. This is the formula that is most commonly used from our side. So you take into consideration your weight, the square root of how much is the T value, and at the same time the root of h. The T is a constant value, which if you require, we can come and see your ladle and use a ladle design calculator and design the entire height, the diameter, the pocket size, the pocket shape, and everything. So this is the impact of having a good sandwich. In the sandwich also, what should be the perfect size? This we have seen the tundish one. So this is an open treatment. You are having a sandwich here, but no tundish. What happens here? This is a real case scenario in one of our European customers. We have a 3 metric ton open treatment. People who are using producing 3 metric ton also still uses ferrosilicon magnesium. They don't use pure magnesium because they have seen the disadvantages of using pure magnesium. They can easily go 3 metric ton is quite big of a size, but they prefer using FSM. But the addition percentage is about 1.8 here in this condition because it was an open treatment earlier they were doing. For them to have a tundish here was quite challenging because the tapping time would increase. So they were worrying about increasing the pouring temperature. All these things has to be balanced. But when we told them what is the magnesium yield that they were having only 45%. So they were adding a lot of magnesium. For 1.8 is a lot of magnesium that was wasted in creating 0.045. But with the correct pocket hole designed, the tundish hole here, we were able to do the same with the cover treatment. The addition came down to 1.3 for the same amount of residual mg, and the magnesium yield came all the way up to 63. So this is the advantages of having a properly designed ladle with a tundish, and we from Elkem can help you in getting this design exactly to your requirement. We don't make ladles, but we can change the dimensions of it in the correct way so that your ladle movement also doesn't get affected. So this is our typical case study. What we develop in our R&D is that you take a 5% magnesium FSM with 0.5% calcium, and the size range is 10 to 25 mm. This is something that we don't recommend, but this size range is most commonly used, not everywhere, mostly in India. So what happens is that if you're doing an open treatment, your addition percentage is about 1.8. If you're just having a pocket inside, you can bring it down about 0.2. If you're having a sandwich, that means that you're putting a cover on top. It's much better. If you're having a tundish, then your addition percentage comes down to 1.3. But if you are able to take a correct sizing, if you are able to take the correct size range, then the amount of magnesium required to get the same amount of residual mg will be lower. As described here, the addition percentage comes down to 1.2. Again, as I told, if I'm able to balance this with a certain amount of calcium, and make sure that I will be calming down the reaction, then I can further reduce my addition percentage and get the same residual mg, and my yield can go all the way up to 80%. So this is the impact of having the tundish, and the impact of having the size, and the impact of having the correct chemistry. For the same conditions what we have, the base sulfur was this much and temperature was this much. So this is the conditions. If you look at it, this temperature also is an effect. Most of you might be aware that when we are superheating the metal, one thing happens, that we know that we are creating not so good metal in terms of nucleating side. At the same time, it consumes a lot of power. So how do you reduce your tapping temperature is also very important. As we were discussing the size effect, so you have a wider size alloy, let us say a 4 to 32 mm, the packing density is much better. What do you mean by packing density? I'll show you a picture. What happens is that you have a controlled and calm reaction. You have a step-by-step reaction. You have fusion reaction. You don't have the lumps simply floating up. And most interestingly, if you are using a wider size, you don't need to use so much amount of cover. Your cover can be 50% of what your alloy addition is. If you're adding 1% of alloy, your cover can be only 0.5. You don't need to add 1:1 ratio of cover, because getting the cover is always a challenge. The correct size, the chemistry, and also getting it uncontaminated is very difficult. So if you look at here, these are the same volume. I have a container in which the volume is the same, but the shape and size is also the same. This is I would say a 10 to 20 or a more narrower one, and this is a more coarser one. This is from somewhere between 4 to 32. It's a big, wider wider sized FSM. You can see for yourself how nicely this is packed and how nicely this is packed. Here, the chances of the metal to go high is quite high. Here, the chances of the metal to go down is very gradual. But people have the misconception that the smaller one can float up very faster. Again, it is the wall. If the ladle pocket is correctly there, that amount of time it takes for it to go step by step will be much slower. How do you quantify this? You can see for visually how much is the reaction, start of reaction, and when is your reaction ending, and how calm is the reaction. This will give you a much not so calm reaction. This will give you a calm reaction. Here I need to have about 1.4% or 1.2% in a good condition. Here I can bring it down to 1%. So this is what happens, the size effect. It makes your process more consistent. Here what happens again, when you are using this sort of a size range, the way they dump it inside, it's again is a challenge. So most of us started using automatic feeder machines. This can always create a problem of inconsistency. Sometimes it can be good, sometimes the residual mg can be low. A smaller or a more wider size range will give you a more stable process, and it will improve your magnesium yield, and it will also reduce your smoke percentage. You'll have very less smoke. And the treatment size. This is a typical thumb rule what Elkem follow globally. If the treatment is about 500 kgs, then we go about 2 to 10 mm. The pocket, we will design it correctly and give it at low addition percentage. We'll give you the FSM with correct rare earth and correct calcium. If it is about 500 to 1000, we use 4 to 25. And the last, if it is greater than 1000, we go for 4 to 32 mm. So this is the impact of size. And the next one is the impact of temperature. So temperature, again, if it is more than 15-20 degrees Celsius, this could be because if you have to pour for longer, you cannot afford to have that end of pouring less than 1350 or 1360. So that what we do, we have to increase the tapping temperature to the higher side. What happens there is that one thing, you have very violent reactions. If you are not using the correct FSM, or if you're using high amount of ferrosilicon magnesium, high amount of magnesium with incorrect calcium value, then the reaction violence is extremely high. It consumes more amount of energy. Most of the mg just keeps evaporating out, and your yield is also lower side, and then money is lost. But if you are able to use the correct size FSM with the good pocket size and shape, I can also reduce your tapping temperature, because my temperature loss will not be that much. Assuming both these ladles have the same lining conditions, they have apple to apple comparison. I don't change the lining. I don't change the way I close my ladle. The ladle is how it is being stationed in between cycles. All these things will impact. So if you look at it, these are the test condition images. This is what we have. So you see here, this is much more violent. This is much more calm reaction. So you have low magnesium evaporation. That is the magnesium that is not being simply fumes generation is not very high. If you see a lot of fumes, you see a lot of magnesium that is being wasted. And the magnesium yield is always higher. When the yield is higher, the consumption is lower, and you have saving on the money. Additionally, a 20 degree to 25 degrees save in your temperature, superheating temperature, that directly saves to money. So this is the impact of having a correct temperature. So if you look at it, this is the brief analysis, how we do the FSM analysis. So everybody has a OES optical emission spectrometer. We get a nice element list like this. Depending upon the capability of the machine, you can have the accuracy of all these elements ranging in different levels. But most of the foundries have this. So what are we measuring here? This gives me an mg of 0.0342 and the sulfur of this much. So what does this mg means? What we are measuring? So this is a combination of dissolved magnesium. That is the magnesium that has gone into your certain amount of iron, certain amount of carbon, and certain amount of silicon. The iron carbon diagram only talks about iron and carbon, but unfortunately, when it comes to cast iron, we have silicon also there. So there will be an impact of silicon. So this amount of silicon, this much amount of silicon, this much amount of carbon, and the remaining iron can take only so much amount of magnesium, which gets dissolved. And the other is the magnesium, which is inclusions. That is the MgS and MgO. Inclusion means these are non-metallic compounds, magnesium inclusions. And the third one is that the magnesium containing slag particles. If you look at it pictorially, so you have the magnesium here, which is created the microparticles, which are quite stable, 1 micron in size, the MgS particles. And then the magnesium that are free. Why it is free? Because it doesn't have enough sulfur, or it has so much amount of sulfur, it just keeps reacting here and then floating it out. It is just evaporating out. So if you look at this amount of time and what is the magnesium here, the dissolved Mg is much more stable with time. The Mg that is with micro inclusions, that is also quite stable. It takes a lot of time for this micro inclusion particles to float out. They will be there only. So it is the amount of excess Mg that is keep floating up. So when you are doing ductile iron treatment, if you're holding the metal for long after treatment, you see a bit of slag that is being generated. So you can remove that and throw it out and start continuing it. The only thing is that this Mg inclusion sites will be there. You need to have a correct amount of inoculant, a capable inoculant, depending upon your casting geometry, to activate that to come to a correct size nodule. So magnesium fading is mainly slag floating and it is evaporating out. The loss of dissolved Mg from microinjection is generally very small. The dissolved Mg doesn't lose. It's very difficult to lose that. Unfortunately, if you're holding for some breakdown, maybe it loses. So this is the hierarchy in which the magnesium loss happens. So if you look at this, the magnesium, what you are measuring here, it is a combination of dissolved magnesium, magnesium that is in evaporating it out, simply going it out waste, and the slag flotation. And again, when we are doing the sampling from the treatment ladle, so since the treatment ladle is here and you are pouring into different pouring ladles, then it is a different scenario. But if you're trying to take a sample directly from the treatment ladle, this is what it looks like. You will have slightly lower stable magnesium here because these are more stable and smaller in size. They will be there. The one that you see on the top are the free Mg that is keep floating up. So we have to be very clear in how we are going to take the sample. But majority of the foundries where I have seen is that they don't use the same ladle for pouring. Most of them put it into different pouring ladles and pour. But unfortunately, if they are using the same ladle for pouring, then the time at which they take the sample is also quite important. So this is very important to understand that the magnesium that you are measuring is not only fully representative. Sometimes you might have a situation where the residual Mg is same for 3 continuous days, and so one day suddenly you are getting 4% more rejections. That is because your useful amount of magnesium has not been performed well. And that can be directly correlated to the FSM quality. How do you correlate the microstructure of the FSM? The microstructure will say what are the phases formed, and it keeps going in backtrack. You can keep completely backtrack it how to control the FSM quality. And the next one is this is just to give an understanding of how much should be your residual Mg and what is the nodal count density. You see 0.04 is good. If you keep increasing your residual Mg, because for some process related issue 0.05 or 0.06 is good, your nodule count will come down because you will see a lot of irregular shaped nodules. You will see exploded, chunky, all these things happening. Your nodule count come down. When a nodule count come down, then the possibility of getting shrinkage, the possibility of getting intercellular carbides, the possibility of getting inclusion kind of defects becomes much more higher. So it's always advisable to have the correct residual Mg, not more than 0.045. In this range is the most perfect target. And again, what happens is that how is your shrinkage tendency? If you are having on the higher side, this both are correlatable. If it goes beyond certain level, then you will also end up getting shrinkage. So it is always not advisable to use the highest amount of magnesium at lowest addition percentage with high residual Mg of 0.06, 0.07. That is also not very mechanically or metallurgically viable process. How do you select it now? So now we have seen the effect of temperature, the effect of reaction violence, the different types of ladles, the different ways you can introduce the magnesium. You can use the pure magnesium or you can use the FSM. So in FSM, for my process, how to select? From your process, you have two aspects we can look at. One is your charge mix and one other one is your process. So the first thing is your process variable, the temperature. If you are having a tapping temperature of more than 1500, it is better to go for hello. Yeah, if you are having a tapping temperature of somewhere between 1480, so lower magnesium you can go for. You can go for a 3 to 5% magnesium, and you can use a high calcium. Your reaction violence will be much better. If your tapping temperature is unfortunately more than 1520, 1500, then for having a better magnesium recovery, a low calcium can be used. Again, these are all interlinked. You have to compromise on something to get the something out. So again, if you're having a height ladle dimensions, if the ladle is not taller and narrower, you are having a wider and a shorter ladle, then the reaction violence and low magnesium recovery. So you have to use medium calcium alloy. And if you have, then you can go for a better calcium alloy, less violent reaction, better magnesium reaction. So you don't need to use so much amount of calcium. The calcium will help to calm the reaction. But at the same time, if you are having a very nice ladle with the 2:1 H by D ratio, L by D ratio, it's both the same, then you don't need to go for a 2.5% or a 3% calcium. Calcium will help to calm the reaction. But unfortunately, if you have more amount of calcium, then it will create more amount of slag also. So tundish cover, if you don't have a tundish cover, it is always advisable to go for a tundish cover. There are a lot of ladle suppliers who are supplying with quick change mechanism. It doesn't take more than 30-40 seconds to remove the tundish. So it is not anymore that it's going to take 1.5 minutes. It's going to eat up my tapping time. It's going to eat up my cycle time. So I have to increase my tapping temperature. A lot of people have developed very nice ladles in India where you are able to remove the tundish cover within less than 60-70 seconds. So that is a very nice options you have to have always to go for a tundish ladle. If you have tundish, it have very little fumes and flare. You have better magnesium yield. You can have lowest calcium in possible, and you can have for a correct size of FSM. If you don't have a tundish cover, then you need to go for a very coarser you have to go for a bigger size of FSM. You need to go for something like 10 to 25, 10 to 32, 4 to 32, like that sizes for a 500 kg treatment itself. And the last one is the treatment size. If it is less than 500 kgs, you can go for a 1 to 2 to 12 mm is the most common size. If it is greater than 500, these are the sizes what we use globally in Elkem. In India only, we do a lot of customizing sizes because the mindset and whatever ladle we have seen it is in like this conditions, but we are trying to slowly change it. So with these are the process variables that you have to take into consideration: your temperature, your ladle, your tundish, and your treatment weight. On the chemistry part, the first thing is your silicon content. Unfortunately, this is the range we will be there. So what you have to use, how which amount of FSM you have to select depending upon your silicon. And the next is the sulfur. So if your sulfur is less than 0.015, you can any type of nodularizing will work. And this is the one we should target. Anything more than that, we should try to control it. If it is something below 0.015, theoretically 0.04, but it is very difficult to activate in 0.04. 0.03 also we can try. Then you need to go for a high amount of magnesium rare earth. And then you need to have a good amount of calcium to calm that reaction. But if you have calcium, then the slag formation will be very high. If you are having a sulfur of more than 0.04, then it is always advisable to do desulfurization before magnesium treatment using FSM. If you're having more than 0.04, then you can try a pure magnesium treatment. Sometimes cored wire also can be tried here. Charge material, if you're using high purity scrap, use nodularizer with low rare earth. Why? Because I told rare earth is used for controlling the impact of subversive elements. So if you're high purity charge material, if you're using, you will not have a lot of trace elements, titanium, chromium, vanadium. You can calculate how much are those in your day-to-day foundry. You can calculate all that. There's something called a Tillman's factor. You can Google that and get that value and see whether it is above 1, less than 1, or equal to 1. So that will give you an idea. If you are using a low quality scrap because of market conditions, because of the type of casting you are making is not sold at a very higher rate, then I need to use these sort of raw materials because at the end of the day, we have to make the money. In that case, you can go for a rare earth one, but you need to have the correct amount of rare earth in it. So these are the selection criteria that we use. The other thing that most commonly we started using in Elkem or started developing in Elkem is our top seed. This is just a replacement to the steel punchings. that is used in the cover. Why do we have steel punching replacement? Why we are doing it is that we are seeing gradually it is very difficult to procure from the purchase point of view, and you don't know what is the composition of all those punchings. And most of the time it is contaminated with oil. We take a lot of care in making sure that the base metal is of good quality, and we do a lot of effort in that. But unfortunately, when it comes to the cover scrap, we tend to overlook it and we put some sort of contamination in it, which will actually spoil your base metal quality. So this is why we have a top seed, which is our ferrosilicon based one. We have different grades of it. The advantage is here is that this is of uniform size and chemistry, so you know what you are adding. You don't need to have any other foreign material that is coming into it, and it is extremely cost effective. Why I would say that here is that people will directly question that this is expensive than my cover scrap, but there are advantages to it which will actually balance your overall cost. If you are using top seed, you don't need to have some subsequent inoculation percentage can also be controlled, and 1% of cover scrap, it takes about 16 degrees Celsius of your heat. Top seed is about 8 degrees Celsius. So if you're using top seed, your tapping temperature can be reduced by 10 to 15 degrees. If your tapping temperature is reduced by 10, 15, then I can reduce my magnesium content. Your magnesium yield also goes high. And also I can increase my, reduce your magnesium addition percentage. So top seed in combination with a low magnesium at a low addition percentage will give you the power, will give you the cost benefit. Also, you will have a power benefit also. You will not compromise on your end of pouring temperature. That will remain the same because the top seed takes less heat to melt and the reaction will be very late. You will not need to superheat the metal so much. The advantage is that it also improves your magnesium recovery. With top seed, we have proven in multiple places the recovery is more than 80%. So people who are using 1.4, 1.3, we have brought it down somewhere between 0.8 to 0.9. That is the addition percentage you can have. And most importantly, it conditions the slag. You'll be able to remove the slag very easily. And it makes your process more stable. So when it comes to the recovery part of it, again with top seed, what happens without cover, you have only 45%, just open treatment. If you're using some sort of a steel cover, you'll get 60%. Top seed, it is always greater than 80%. So this is a very realistic data that we have generated. With FSM, as I said earlier, open treatment 1.8, you put a pocket, you put a sandwich, tundish, and top seed is always less than 1. How do we optimize the top seed? We just don't sell the top seed alone. We go see the treatment ladle, we see what is the correct shape and size of the pocket, and then we design the pocket. We have a pocket design calculator. What should be the correct shape of the pocket? Can it be circular? Can it be semicircular? Can it be a filled corners? And then how do I orient the pocket? Where do I keep it? Do I keep it to the side, or do I follow this sort of a mechanism, or do I have it at the center? We can calculate all these things depending on the process. We can calculate what should be this height in your tundish capacity, how much it can hold, so that you have a very uniform flow here. All these things, if we can go in detail and check, which will make sure that your recovery is on the higher side. You can use the least amount of magnesium. In the least amount of magnesium also, you can use the lowest grade of magnesium. So this is with respect to the recovery. This in-mold FSM is the next part. This is something very not so common in India. Only few people are doing. You have a reaction chamber inbuilt into your gating system where you keep the ferrosilicon magnesium into it. You put a filter and the casting is there. So there are different orientations possible. And then this reaction chamber has to be designed very specifically so that it will be able to accumulate that amount of material. So it gives you a recovery of 85%. Interesting point here is that you don't need any, you don't need to have a lot of fancy deslagging setup here, because the FSM that you use has to be of correct size and correct shape and correct chemistry. If you are not using that, then it becomes a headache. You will end up getting a lot of slag, draws, all these issues. So it don't have any fumes in this process because it is inside the mold, and it doesn't require a lot of capital investment. You don't need to invest on a ladle, you don't need to invest on people, training people, but it has very minimal environmental impact because the fume generation is very less. It also, the drawbacks here is that it kind of reduces your casting yield. In a particular here, if you have a ladle FSM treatment, you can put one more casting here and improve your casting yield. And it requires a lot of process consistency. Your base sulfur needs to be extremely controlled. Your amount of trace element needs to be controlled. And then you need to do 100% quality inspection of all your castings. So these are used for special types of castings, low volume castings, but which needs a lot of critical applications. That is where they use in-mold FSM. The last part is the code wire. So code wire is not something new. It has been there since long. This is a typical schematic of a code wire plant. You have the same ladle, a tall narrow ladle, and then you have a wire feeder, and then it is enclosed in a chamber. So one of the advantages of code wire is that precise addition of magnesium based on the exact tap metal weight. most of the foundries, they tap for melt 500 kgs and then melt 1000 kgs and then tap 500, hold the remaining 500 and then tap the again. So they don't know exactly how much is being tapped. There's always a plus or minus 50 to 60 kg and the addition percentage, they have to compensate for that. But in code wire, they claim it is a very precise addition of magnesium and it is environment friendly. There is no visible fumes and it is fully automated, no manual weighment, addition and compaction of FSM inside the treatment ladle pocket. These are some of the advantages that are claimed. But as I said, these are claimed advantages. This all can be challenged. In reality, all this will be questioned. What is the major concerns of code wire is the quality issue. You never know what is the homogeneity of the wire inside. This is the wire sheet, the powder and the iron that is mixed inside. You never know what is the homogeneity of it, how homogeneously it is distributed throughout the coil, what is the quality and how good is the density of all this. Again, there are code wire suppliers who are exceptional. They have laser guided machines who can help you in all these things. But the ones that are very commercially available and now being pushed, you have to challenge all these things. And it is very difficult for you to test it also. The raw material traceability is also not known. The brittle and the wire can break away easily. These are some of the things because the wire is being pushed from the top. It is not always guaranteed that it is going to the bottom. Sometimes it can dwell like this. Sometimes it can get cut also. So you never know the entire metal is getting homogenized. So this is something that we have prepared. But if this is just a small case study, what we have done, you take 100 tons of casting you are making. Your casting yield in code wire will always be lower. Why do you have a lower casting yield? Because the potential of casting defects is higher. You would see carbides, you would see shrinkage, you would see dross, all these sort of things coming up if you're shifting from FSM to code wire with the existing gating design. So typically they advise you to, or the solution is to put the number of chills or increasing the thickness of the gating. But in this case, even if you are reducing your casting yield by 2%, the cost impact is too much. You can see for yourself how much is the cost impact. But typically this is the cost that the people look for the code wire. Code wire addition percentage is 0.6 and code wire rate is 240 or 250, whatever it is in the market. My overall treatment cost for making 100 tons of casting is only this much. But if I put FSM 1.1%, which is on the lower side, and I buy it at 180 rupees, and still my treatment cost is almost this much. But you see the difference between these two costs and these two costs, your overall final cost will change. Okay, some people say that, okay, I will not compromise on my casting yield, I will maintain it 60%. Then you need to add a lot of inoculant because code wire has 25% magnesium. It will so much amount of magnesium will need a lot of inoculant. If you're not, and a lot of high potent inoculant, which are expensive. If not able to manage that, then your carbides, your shrinkage and your dross related defects will be again at least going up by 1 or 2%. That is again the direct cost. Code wire, you need to increase the tapping temperature because the time it takes for it to plunge is much more. So these are it. So if you look at the overall cost of code wire for a small setup also, taking into consideration the end-to-end picture, not only the treatment cost, it is always on the negative side. What it does, because of the casting yield, the magnesium recovery is also lower. You need to increase the tapping temperature. The last one, in terms of defect, it creates shrinkage, dross, and carbides. These are the three things that you have it in it. But for some castings where you need to have this particular, where you don't need to worry about the casting yield and you need to save on certain aspects, then you can think about code wire. But on the larger scale, it is not a very viable process of doing modularization. It has been there for quite a long time. Most of the European market, they are using it, but we have seen in Elkem recently also we have converted. Again, this is the last part. Code wire is not also an environment friendly process. They say that you don't see any visible fumes. Sir, I'll finish in 2 minutes. The code wire is not an environment friendly process.
Voice, you can, yeah.
Sorry, sir.
Oh, you can go ahead. I think some cross.
Okay, sir. Code wire is not an environment friendly process. Why I'm saying is that the code wire consumes a lot of magnesium. In you're using ferrosilicon magnesium, you are using 7% magnesium. Code wire uses 25% magnesium. On top of it, the code wire recovery is always 40% lower than FSM. So for producing 100-ton casting, you have to use more amount of magnesium. More amount of magnesium needs to be mined out, and more amount of magnesium when you are using, majority of it is also wasted as fumes. So that fumes needs to be collected, extracted. What are you going to do with that fumes? A lot of challenges there. So on the environmental front, code wire is not at all a very environmentally cautious thing. That is why in Elkem we always deliberate with code wire, because it is not something that is new to us. We have been there in code wire. Because of this particular aspect only, we are not very keen on it. and process efficiency of ductile iron. So reaction violence, this is just the summary of it. It should be on the lower side. I want somewhere my reaction violence to be low. High, I don't want. On the fumes and slag generation, I want it on the lower side. I don't want a lot of fumes and a lot of slags. So I don't want to be in this region. I don't want in both of these parameters to be here. And then on the magnesium recovery, I don't want low magnesium recovery. I want high magnesium. So I want to be here. So, and then on the inoculating effect of my ductile iron treatment, I want to be high. So if you look at this particular area, I want to be somewhere here. I don't want to be somewhere here because this is negative, negative. This is also negative. This is also negative. All the axes I'm getting negative. So if I plot a basic chart, if I use high and pure Mg, unfortunately, I will be in this side of the area. If I use a low Mg alloy, which will have a very good magnesium recovery, good inoculating effect, reaction violence is low, slag and fumes also will be low. So I want to be in this green. Converter, unfortunately, it is higher. Code wire, it is somewhere here. Sandwich, this is where most of us are here. Tundish, sandwich plus tundish, this is the best. And in mold, it is the best, but unfortunately, a lot of process control in India, I've seen only 2% doing it, and they don't produce a lot of ductile iron, so they do it. And the amount of quality and the amount of, the control required is very high. We design the pocket chamber, we constantly keep changing it, but that is one of the best because we use the least amount of magnesium there possible with a very smaller size. So this is the ductile iron whole treatment options available. Each of it has own cost, benefits, and savings. If you look at it, this is just to show what Elkem can offer you at the moment. So you see any casting has two parts. We have the design part. That is every casting starts with the design, and then you have the metal part, and then you have the sand part. So Elkem is more associated with the metal part. Both these has to come together. You make the casting, fiddle it, and you sell it and make money. So when it comes to the charge material, we have our carburizers, which is extremely controlled amount of sulfur. We have our ferrosilicon and silicon. Elkem as such is a silicon company. We make silicon that is used most of the solar panels. It's used in semiconductor industries. All our mobile phones at least have 2 to 3 grams of Elkem silicon. And then Elkem carburizer, we have Elkem pre-seed also, which is our preconditioner that goes directly into your melting furnace. If you are adding preconditioner, you should not have fading. If the preconditioner, any preconditioner that you add, it should be added along with the charge mix, not towards the end when the metal is red hot condition. If you're adding in that condition, that is not a preconditioner, that is just a pre-inoculant. Again, for ductile iron, we have our magnesium, which is called LMAG. We have our lanthanum-based magnesium, and then we have our compact mag, which is used for our FSM, for CGI. And then these are the various inoculants. I'm not going in one by one because of time constraint, but we have inoculants varying all the way with different elements for different applications. FSM ranging with different combination of magnesium, rare earth, as well as calcium. So we have to select the correct one for the first, for your application. Again, we do have a thermal analysis system. We do offer this as a service to our customer. We don't sell this equipment because thermal analysis allows us to measure the graphite growth. The drawbacks of having OES, you never know how are these compounds interacting. But thermal analysis is not anymore a research project. Most of them use it in the shop floor. It kind of helps you to measure the graphite growth and predict it. It's a predicting science tool. It cannot very accurately say what is your rejections percentage, how much should I add, how much should I, all this. Those are all predicted value. They have some sort of logic and mathematical calculation behind it. But with thermal analysis, we can measure only these major 4 points. Based on that, you need to know how good is your base metal, the impact of raw material, charging, holding. Do you need preconditioning? What should be the inoculant? What should be the FSM? All these can be more systematically measured and predicted. So for predicting it, you need to have a good understanding of it. That is why we have our own thermal analysis system. We have a team, we sit and dedicatedly observe it and continuously improve it. And then we have logical conclusions. So this is on our services. So we do have our lab in India. We have opened our R&D in India and Nagpur in 2020. For the first time, we have moved out of Norway and started an R&D here. We have our technical customer service lab. We do offer our OES, which is highly top of the line machine with all the CRMs we have. That is the most important. Our machine is more stable, standardized. So we can check trace elements very accurately. We have a scanning electron microscope, both in Shanghai as well as in Kristiansand. More importantly, we have a very capable team for analyzing the SIM because we do a lot of defect analysis for our customers. Mostly SEM is just a tool. You need to interpret what it shows. You need to have correct people. We have almost people with almost 40 years of metallurgical experience doing this aspect, doing this defect analysis. We have a carbon sulfur analyzer, oxygen nitrogen analyzer, microscopes. This is our technical service report. We do offer our anti-segregation bins, and most importantly, we have a very strong technical team. Globally, we are about 25 people who are part of technical team, as well as in the R&D, we are about 8 people. We frequently meet, interact, and exchange ideas. That is why we are able to uh, come up with some products, some innovation solutions that can help the foundry space to at least save 2 or 3%. Because in India at the moment, what we feel here is that we are there up to 80 to 85%. Going beyond that is always a challenge. 1 or 2% here and there needs a bit of focused effort. For that focused effort, we can always help. And we can always come visit your shop floor, assist you in selecting the best package. At the end of the day, it has to be in green. The money has to be there. You need to see if you're using our product, you need to save on your money. So that is where we focus. So I would request everyone that give us an opportunity. You can contact any of our sales team. We will be more than happy to visit you and then further see how we can help you. These are some of my colleagues who help in creating all our content, my team members. So I just like to acknowledge them. And that's it from my side. And I would like to really apologize for the net interruptions, but I hope this was clear this time.
Mr.
Yes, sir.
Balaguru, it's really fantastic presentation. Now I'd request participants. We have already reached 4:15. Maybe we'll spend as small as time possible for the question answer session. If any questions, please unmute yourself, ask question, or post your question in the chat box. Yeah, I think already some questions have come. Yeah. Sir, please
Sir,
introduce yourself.
Sir,
Please
I'm
introduce
Vinay
yourself.
Desai. Hello.
Yeah.
Hello.
Yeah,
Yes,
tell me,
I'm
sir.
Vinay Desai from Kolhapur.
Yes, sir. Tell me, sir. How are you, sir?
Fine. Sir, we have started a small foundry. My son has started a small foundry, and we are pouring 670-gram castings. That is ductile iron 500 by 7 for camshaft, small camshafts in shell molding. And we are facing a problem of carbides at the periphery of the lobe. Hello.
Yeah. Mr. Balaguru, are you
Yes,
there?
sir.
Yeah,
Yes,
you
sir, I'm there,
So
sir.
do you recommend any preconditioner for that? It's a shell molded
Again, sir,
casting.
again,
We
it's a very generic. It's a very generic question. So, if you, I would really not give you a solution here. I would collect more details. You can Kolhapur. We have Pratik, who's our Kolhapur person. I would share
okay.
his number in this chat. You can contact him.
Please.
We can help you, because if I say something here, that needs to have some logic to it. But with minimal data, I typically don't recommend, sir.
Yeah. Yes, sir. Yes, sir. Please.
So we have two persons in Kolhapur. Pratik is there. Akshay Kamte is there. You are in which
Yes.
MIDC, sir?
Kagal MIDC.
Kagal. We can come and visit you, sir. We have
I know.
yes, sir.
I know Akshay. I'll be calling him in a day or two.
You call him, sir. I am the technical person there. I can come and help you there. No problem.
Okay, sir. Okay. Thank
So
you.
thank you, sir.
Yes.
So there's a question from Mr. Mohan Raj. I don't know. Can't get the presentation. So this will be hosted in the YouTube. You can check it later. Will smaller alloy in bottom and bigger alloy at top will help improve the reaction? How sealing?
तो म्हटलंय दुसरीकडे काम आलंय सर इथं निघतात
Hello. Sir, if you want
Sir, I
any
get the
question,
question.
yeah, please introduce yourself and ask questions, sir.
Sir, to answer the question of will smaller alloy in the bottom and bigger alloy on the top help to improve the reaction, because the surface area of smaller alloy will be more, which will support delayed reaction. That is, reaction will start after sufficient amount of liquid is filled. So with smaller in the bottom and bigger in the top, again, how do you ensure that this is going to happen? 100% is the challenge, because these alloys, you need to have separate bins, and if you're able to ensure them, then we can try this and see how good it will be, sir. But the best practice is to have, while we have, I'm saying a wider one, not smaller or bigger, 4 to 32. You have different sizes so that when you drop it inside, it's all packed densely together. You don't have enough spaces between two particles. So if you have all the coarser at the top and all the smaller at the top, then again you have the chances of the gap between the coarser will be much higher. Ideally, I want those gaps to be filled by having the smaller sized FSM in 4 to 32 mm. So that is why I say that we should have the most wider range of FSM available to be used. If you're using that as an added advantage, you can come down on your cover additions.
Sir, good evening. I'm Chandrasekhar from VR Foundry.
Yes, sir.
Yes, sir.
In defect analysis, suppose if I have a slag defect, in your R&D facility, can we find out that slag is whether due to metallic slag or non-metallic slag or sand is related slag? Can we find it out in your laboratory?
Yes, sir. We can definitely do it. Slag as such is a very, very complex thing. For slag itself, we can have a separate session I can present for 2 hours. But we do a lot of slag analysis from different locations in the foundry, from furnace, from ladle lining sticking, from pocket. So we can check what is the slag. It's acidic, neutral, or basic. Based on that, we can classify whether it is a slag or a dross. A lot of things we can check. You can send us the sample. We can check, sir.
To whom should I contact? I am in Coimbatore. To whom should I contact, sir?
Sir, which area, sir, you are from?
Coimbatore VR Foundry.
Coimbatore. Hello?
Yes, yes, Coimbatore. We are Foundry.
Sir, if you are from,
Yeah,
sir,
yes, sir.
if you are from Coimbatore, you can contact Shankar or you can contact Srinivasan, sir. We have 2 persons there.
Okay, okay.
Shankar, sir, is there in the
Yeah.
meeting, so he has seen your request, so he will contact you, sir.
So they are a salesperson, we can contact them.
Yes, the first line of contact for us is sales will then give to the TCS to the R&D, sir. It's the
Right, sir. Thank you.
So there is a question in the chat box. How to decide mg packet diameter and depth in the treatment ladle?
Sir, can you please repeat? I didn't hear that.
Yeah, the chat, there is Anuj has given a question. How to decide mg packet diameter and depth in the treatment ladle?
Yes, sir. How do you determine is basically first, what is the treatment size you do? That has to be the first consideration. 500 kg, 1000 kg. What is the ladle you have? What is the length and diameter you have? If you are having a tundish or not. If you are having all this correctly, then you need to see which is the best way we can have it. For that only we have a ladle design calculator. We can help you in that, but in general, the parameters to consider for selection of the pocket shape is that the size range of FSM that you are using. And what you should look out for is that you should use the wider size range. You should use the least amount of FSM and your reaction should start as late as possible. With these two set condition of using the least amount of magnesium wider size range, you can keep changing the ladle pocket shape. You can make it wider, taller, narrower, whatever, and you can achieve at it. But if you want a more structured approach, you can approach us. We would disclose it how to do it, sir. Because that is again, it is our IP product, so that we don't disclose it in open forum. But you can approach us. We can help you in that.
Yeah, Balaguru sir, I have my own question. I think you know very well that we are somewhere associated with this particular treatment, and we supply solutions for basically for SSM treatment, for automation. For I think I saw that benefit you have shown that core wire has got a automatic payment. Even now is FSM also has come that solution. That is there, but
Yes, sir.
Of late I'm seeing, but more importance given for core wire treatment.
Yes, sir.
I've seen a couple of people, couple of projects which recently last 2 years time. Many people have gone towards the core wire treatment. I have seen your differentiators. Is there any specific advantage why it is going, or is there any? It is the people are not educated, or people are not their awareness is not reached. But I was told that internationally this treatment is used widely. What is the fundamental difference?
Sir, if you look at cold wire, as I said earlier, it is not new. It has been there since 70s.
Okay.
It is as far as FSM, as ladle treatment. It has never caught on in Europe as well as in America to the extent as ladle treatment, because you need a lot of process control for it to work. As the advantage is claimed, one is, again, if you look at the real impact, it is not really. One advantage what people can claim with cold wire is that the automation aspect of it. If you look at it, if you're having FSM, it needs to be comes in bags, it needs to be stored. You need to have a person for weighing it and then putting it in a pocket. It needs to be compacted. All these tasks are there. But as you rightly said, we have alloy dispensing machines which can take care of that. And I think you are one of the pioneers who can do that. So this benefit has been completely eliminated. The one that you see suddenly rising in India is mainly, according to us, whatever analysis we have done, is just because of the cost benefit. The cost benefit, only people look at the treatment cost. People who do not require the complete package cost, they do not take into consideration how much of a casting yield it has taken a hit, or how much has the metallurgical rejections gone up. And all this will not visibly happen. If you are using code wire, first couple of months, you will not have that much. Slowly, when the code wire keeps the trace elements keeps building up in your system, I mean, in your returns, that is where you see a problem. So if you consider all this whole scenario, you will not see it as a very viable process. One one aspect why it is gaining momentum here is that it's most of the customers of foundries demand, they want to have very little fumes in the shop floor. And core wire as such doesn't generate less fumes. It generates a lot of fumes, but it is having a very nice suction method. So that is the reason what I think is the logic behind why people are asking for code wire. But if you take the great picture of it, not environment friendly, the only benefit is that the automation, or I mean the automation aspect of it. For that, you are there to give us the best solution. And on the last part of it, when you are saying that it can remove all the fumes out, it is better to stop the generation of the fumes with the correct magnesium.
That's great. That's great. I think one more gentleman, Mr. Selvaraj, which magnesium process is best for better MG recovery, cold wire or sandwich? I think that's what we discussed now. Yeah.
Yes,
The next
sir.
question
Cold
is,
wire will not be good. In cold wire, the magnesium recovery will not be good. The magnesium recovery will be lower because cold wire uses 25% magnesium. A lot of is wasted in fumes. If cold wire is giving you an excellent magnesium recovery of more than 80%, for a 25% magnesium percentage, you will add 0.2, sir, not 0.6 or 0.7.
okay. So the next question, I think MG reaction time after a tapping. What is this question? I don't know whether they're asking
It
what is
should
the
be as
reaction
late as possible.
tapping. Huh?
If
Sorry.
they are tapping for, let us say, 50 seconds, I would suggest that you have the start of reaction at least after 30 seconds. So you have to make sure that it is starting as late as possible. How do you ensure? Have a tundish. Make sure that the tundish bottom hole is of the correct diameter as per the formula, and have the correct pocket shape, and then use the correct FSM, minimal cover, and you will be able to achieve it. If you are having any challenges in it, you can call us, we can help you.
Okay. Gentlemen, any other questions? If there are no questions, I think we are reaching 4:25. If any questions, I think no more questions, we can close our session. This timer part, what you answered, it said 50 seconds means 30 seconds is the starting time. But some places, people, I understand, people go based on the weight. Is the right method?
Weight is the correct method, sir. But again, if you are having 500 kgs and you are tapping for 50, then you know what is the rate per kg, rate per second. So you can calculate. If you are having the weighment, that is also a good option, sir.
Okay. Because we
But I
also
see
supply.
weighment in most of. Yes, sir. You are supplying. I see big foundries, they have weight control, but smaller foundries, stopwatch is much more easy and affordable at the moment. So that's why I said time.
Okay, I think there's a last question. In sandwich method, how much steel should be above and below the MG?
Ideally, you should not put any mg below it, but what happens is that once you add the alloy into the treatment ladle, you should not keep the treatment ladle idle for more than 2 or 3 minutes. If you are keeping it, then the mg starts to fuse. That is why people typically tend to put a bit of alloy, a bit of cover scrap at the bottom as well. So that is not a very recommended practice. It is always recommended to add the alloy just before the tapping. When the person is inserting the thermocouple or IR gun to measure the temperature, you can add the alloy and take the ladle up. So that would be the best practice. If not possible, then add the least amount of scrap at the bottom. And additionally, I would like to say here is that when you are doing after treatment, when you are emptying the ladle, please tilt the ladle as much as possible to drain the metal out, because there will be slag at the bottom, and the slag, if it settles in the pocket, that is a risk. The pocket gets damaged and the lining has to be changed. So if possible, completely tilt the ladle and drain it out. If you're doing this, then you no need to add scrap at the bottom. On the top, I would say not more than 50% of your addition percentage of FSM or scrap.
Okay. Thank you. I think we'll go for a closer, sir. Thank you very much, Mr. Balaguru. I think it is indeed one of the wonderful presentation, and which can be seen by the people who have attended. I could see one point in time it is crossed more than 85, and many people, generally in Chennai and around Chennai, people watch this webinars in their conference room. That calculation, it would definitely would have reached more than 150 people. And this is one of the good seminar, and I think the content what you have covered is also in depth. I think people like me who was not, I know about the process, but I know it is only treatment, nothing else more than that. But you talked about in basics and what are the parameters involving. It's indeed very, very in depth, and I think people definitely must have taken a lot of takeaways. Thank you very much for spending valuable time and educating our participants. And I'm also thanking Elkem for this great opportunity. And then I also thank all the participants who took the time to attend this webinar and that busy schedule, and your participation motivating us. And we from Chennai chapter conduct regularly weekly webinars, and our second week webinars we jointly with Southern Region we conducting it. And for your information, all our webinars and seminars are hosted in our YouTube channel. In later stage, if you want to refer it, you can go to IF Chennai Chapter YouTube channel and then refer and get benefit of it. And thank you once again for everyone. Thanks for valuable time. And we'll meet at the next webinar, and the announcement will be given to you on time to time. Thank you, sir. Thank you, Balaguru sir. Shankar sir, thank you. I hope you enjoyable.
Thank you.
Thank you.
Thank you, sir. Thank you, sir. Thank you, Sendil sir. Thank you.
Thank you very much.